Hello, today we'll be going over a midterm question from summer 2020. Ham operators use a long wire as a long wave antenna. Consider a long horizontal wire of length L, which we can assume to be infinitely long, and it's at a height of h above the ground. And when we say ground, we mean the ground plane. First, find the magnetic field in the loop above the ground. Then we're asked, what is the surface charge density on the ground? Okay, let's answer the first part first. It states, find the magnetic field in the loop above the ground. Now, when we think of magnetic fields, we need to think of Ampere's law. Ampere's law states that if we have our magnetic field dotted with our dl, our loop, it's equal to mu naught I being our current. Now, similar to Gauss's law, we can simplify this expression so we don't have to do this complex line integral. We can simplify if we meet two conditions. The magnitude of the B field is uniform on the contour, meaning within our circle, and also the direction of the B field lines up with the contour, so the dot product always equals 1. So when we simplify this, we get BL, our length of our loop, equals mu naught I. Okay, let's think about how currents travel in a wire. When we see this I here traveling to the left in this wire, we can use the right-hand rule to figure out how the magnetic field looks. If our thumb is pointed to the left and our fingers wrap around, we know that outside the magnetic field is coming at us, and inside the magnetic field is going away from us. So we can figure out which direction this magnetic field is going. Now, what we're going to do for the loop is we need to think of it as a circle around our wire. And when we think of circle, we think of perimeter of our circle or circumference. So to simplify this expression a little bit more, our B is multiplied by that circumference, 2 pi r, and it's equal to mu naught I. We take this one step further, then we have B equals mu naught I over 2 pi r. And these are vectors. Now, we don't know what our R is yet, so we need to figure out that, but that'll come next. But now, we need to understand what's happening to this wire being above this ground plane. When we think of ground plane, we can think of it as a mirror. So what we do is we replace the ground plane with our image charge. So we can literally draw exactly what we see like a mirror with our image charge. But we note that in the image charge, the current is in the opposite direction as it is on the non-mirror charge, the original image. So with that being said, we know that our image charge is going to the left. Again, if we point our thumb that way and use our right-hand rule, our fingers would curl around. So again, on the inside here, our magnetic field will be going into the page, and on the outside here, it will be coming out of the page. Now we do have these legs on the left and on the right with their own magnetic fields looping around. But in our example here, in our problem here, it says we can assume this line of current to be infinitely long. So if they're infinitely long, we don't need to take those two legs into account. And also, since it's infinitely long, we could position our point in question directly between the middle, and so you could say that the magnetic fields would cancel, but we don't need to include those in our calculations. Okay, our next step is to figure out what our R distance is. So if we pick a point, let's say this is within our loop, and we call this our Z point. We know that the very top here is H. And also, likewise on the bottom, this distance is also H. So on our top section, we have this H distance, but then we need to subtract this z distance to get our radius. So on the top here, our distance would be h minus z, and that will give us this point right here. Also on the bottom, we have this h distance from our bottom line to the center here. But our radius is actually plus this z distance here. So the contribution, or r, from this bottom current wire is going to be h plus z. Okay, and that will give us our second r distance. So now what we can do is we can plug that into our B field. Again, we're going to have two contributions to this B field. We're going to have the contribution from the top wire and from the bottom wire. So our B is going to be mu naught I over 2 pi. Let's do the first one, the top one first. H minus z, and then plus, again, mu naught I over 2 pi h plus z. I think I said minus on that one, but one is going to be the minus and one is going to be the plus. Okay, and now what we'll do is we'll simplify this. Mu naught I is going to be 2 pi, and I'm going to let you do the algebra on this, but this is going to equal 2h over h plus z, h minus z. And again, if we take this one more step, we're going to get mu naught I over h pi h squared plus z squared. Okay, but now what we need to figure out is what direction our magnetic field is pointing. Well, we said that both contributions of this magnetic field are pointing, oops, and that's actually a minus. Sorry, this is a minus if we FOIL that out correctly. Both contributions are going into the page, and if we look at our coordinate system here, x and z, we know that into the page is going to be a positive y hat. So we're going to add that here to the y hat, and again, this would be into the page, so we'll make a little reference of that. Now that we have our magnetic field defined, we can move on to the second part of the question. What is the surface charge density on the ground? To do that, we need to remember our boundary equations for magnetic fields, and the one that we're going to use is N2 hat, oops, this is a hat, crossed with H1 vector minus H2 vector, and that will equal our JS, or our surface current vector. So what is N2? N2 depends on how you look at the system. In our case, we're going to define N2 as the normal from the second medium. So if we can imagine this ground plane, part of it is coming out at us, the other part is going in at us. This is in the y plane. So our normal to the y plane is here, is z, positive z. So our normal 2 is going to be z hat. We need to define which normal we're talking about, because that will help us to define what our H1 and our H2 is. And since our N2 we're defining from this ground plane, we know that then our H1 is going to be up in the air where we've already found our magnetic field. So now they're asking, what is the surface charge density on the ground plane? So what does that mean? That means literally on close to the ground plane, on top of it. So since our z, as we go up, is away from our ground plane, we're literally asking, what is the magnetic field when z equals 0? So if we make this z equal to 0, our B field will be mu naught I h over pi h squared. We have that h we can cancel, so our magnetic field will be mu naught I over pi h. And again, this is in the y hat direction. Great. So now we have our B field right on the surface. But the question needs H field. So the way we relate H and B fields, H field vector is equal to the B field vector over mu naught. So in our case, let's plug that in. We have mu naught I over mu naught pi h. These mu naughts will cancel. So we end up with I over pi h, again in that y hat direction. And this will be our h1. Perfect. So let's plug that in. So now we have I over pi h, and that is in the y hat direction. Okay, now what is our h2? Since this is a ground plane, we need to remember that the E field and the B fields and the H fields, for that matter, in a ground plane will always equal 0. And since we defined H2 to be in the ground plane, this will equal 0. So that will help us out. And this will be equal to our surface current density. Next, we need to think about what direction is our surface current density. We have a z cross y. So a little trick to find out what your cross product results will be is this. I make a little x, y, z, and if you go in the clockwise direction, you will get a positive answer. So if we had x cross y, it will have a positive z. If we go in the negative direction, y cross z, that will give us a negative answer, counterclockwise direction, you'll get a negative answer. So let's think about this. So now we have z cross y, that will give us a negative x answer. So we know that our surface current, let's just put it over here to remind us, will be a negative x hat direction. Now we're ready to go. We can disregard the cross product. We figured out the direction, so now we can simply multiply, and we think of the z as a 1 multiplied by our y hat number. In this case, it will just be that number. So what we can do is we can write our surface current will equal I over pi h, and this will be in the negative x hat direction. Let me just simplify that a little bit more so we can see it a little bit better. Great. And this will be the negative x hat I over pi h. Great. And that is our answer. That is our surface current density. So again, to recap, to find the magnetic field, we need to think of Ampere's law using our B.dl that we can simplify to use our Ampere's loop, similar to the Gauss's loop. We figure out where that is, what our R is. Once we do that, we can plug those into our B field equation to find out what our B field is. Then we use our boundary condition equations. We find our B field when z is 0, convert that to the H field, find out what our normal vector is, define our normal vector, plug it in, and that is how we get our surface current. Thank you.